We are still in the chapter of statistics, and we discussed part one of statistics chapter in our last lecture. And today we will talk one more time about linear regression. I believe linear regression is not a new topic for you. If you remember, we discussed in chapter 5 about the first method of drawing linear regression manually, and we defined linear regression as the study of the relationship among variables. You have a set of data that you gotta draw on the Cartesian X and Y. Those data, you're trying to understand it. As we mentioned, human is a visual creature, so it's easy for you to visualize and draw conclusion out as you're drawing the data in graphs format. And as a more or a next step further in linear regression, you got to draw a line that will represent the trend of the data. If you have some variable on the x-axis, another variable on the y-axis, and you have points x1, y1, x2, y2, x3, y3, then you want to say as x increase, does y increase or decrease? Then you can see the overall behavior of the data. Is the data increasing or decreasing, increment or decrement, and draw all the conclusion needed on a physical or a mathematical variables that you're trying to study at that point. The simplest and most used equation is the linear equation y equals m multiplied by x plus b. You remember that, and we call it linear regression because we are handling linear equations, and if we have any equation different than that, we try to bring it back to the linear format to be able to do the regression for it. Otherwise, linear regression will not be the best approach to be able to conclude and draw your results about the data. And remember that we said m and b are constants in that equation. When you find m and b, then you can know the relation between the x and the y variables. X could be the temperature, y could be the pressure, x could be the speed, y could be the engine power, and so on. Now let's imagine that we need to study the relationship between the car age, represented as the x values, and the annual maintenance cost, represented as the y value. Now, as you remember, we first collect the data, then we plot those data on the xy coordinate, which is called mathematically the Cartesian. So the age of the car on the x-axis in years, and the annual maintenance cost of that car on the y-axis. And when you draw the data in this format, now you call this as the scatter diagram, because you draw the data as points that are scattered along the x and the y-axis. After that, we draw the regression line following the methodology. We said there's two methods of drawing the regression line. The first method is what we call it as the simple mode method, which is manual, where you draw the line and make sure the right-hand side data points equal to the left-hand side data points, and you start at a certain point and you end at a certain point or close enough to it. Then you find the equation of that line. That's the whole point. When you find m and b as the constants of your equation y equals mx plus b, then you found the equation of your line regression. After you do that, then you can study the behavior between and the relation between these two variables. So in this case, it's obvious, as the car is aging, the annual maintenance cost for that car is increasing. That's the conclusion you can draw, which makes sense, and you experience it in your real life experience. Now, again, the two famous ways of drawing the linear regression are: the first method is selected points method, or the manual method. That's what we studied in chapter 5, where you draw the data manually and you draw the line following a certain procedure and quotients to be able to draw the line in the most logical way. The second interesting method that we promised we're going to discuss later, which is now the least squared method. This is another mathematical based method to draw the regression line. It could be useful in some applications, while selected point method could be useful in other applications. Mostly selected point method is used when you have less amount of data and it's possible to draw the data and the regression line by hand, while the least squared method is more of a coding friendly method. There's many applications, scripts, and softwares been written to find the least squared method. Of course, there's many softwares can do that for you, but we want to teach you how to do that mathematically and manually. At least you know what's the concept behind the least squared method. Now, to be able to understand how the least squared or squares line is fitted to the data, we need to assume that we have a class of 20 students. We brought these 20 students and gave them a math class, a math exam and an IQ test. IQ test is a test to test how intelligent you are. I don't want to argue here how efficient is that, but it is a test available today. Now, we have n pairs of numbers. We have points x1, y1, x2, y2, all the way to xn, yn. And n in this case is 20. So the number of samples, 20. We have 20 students. Now, x will represent the IQ or the intelligence measure exam, and y would represent the math scores. Now, we need to assume that the equation of the line that fit the data is y star equals mx plus b. Now, we studied before y equals mx plus b. The difference between y and y star in the least squared or squares method, you have an observed values and calculated values, and you try to make the difference as minimum as possible mathematically between the observed values and the calculated values. That's why they call it the least squared method. You try to minimize the difference between the observed values and the calculated values. So back to our linear equation, y star, calculated values, equals mx plus b. Our mission to find m and b so that we can find the calculated value regression line and compare it with the observed values. And the closer you are to the observed values, the more accurate or the more efficient your least squared method is, and the more realistic your regression line is in this case. Now we have here the students 1 all the way to 10, the math score 85, 62 all the way to 80. The IQ for student 1 is this, student 2 is that, and we continue 11 to 20, math score and IQ. So we have 2 columns, student number, 3 columns, student number, math score, IQ test score, all the way from 1 to 20. Now, the least squares method needs to find the sum of all y minus y star. So the observed minus the calculated values of I, and that needs to be the smallest possible. Then we determine the values of m and b so that the difference between the observed y and the calculated y star will be minimized as described earlier. Now, when you try to draw on the Cartesian, so you have the IQ on the x-axis from 0 to 160, you have the math score from 0 to 125. So you have the x-axis here, y-axis here. Then you try to draw the line. Here we would say y star equals mx plus b. By the way, your textbook is using prime instead of star, but I think instead of confusing with differentiation, I think star make more sense. Then you plot your points and you draw your regression line between those points. Now, there is an equation to find m and b with the least squares method. M would equal n, number of samples, multiplied by the summation of xi, yi, which means you go x1, y1, plus x2 multiplied by y2, and so on. Then you do the sum for all of those multiplications between x1, y1, x2, y2, and so on. Minus the summation of xi, whatever the value of x, in this case x is IQ, you go to that and you do the summation for all those values. And you go for yi, which is math scores, you do the summation for all of them, then you multiply both summations. Divide by n, multiplied by the summation of xi squared. So you go to each point of IQ and you give it a square, then you go to the next value, give it a square, then you add them all together. That would be the value to substitute here. Minus the summation of xi, you do the summation first of the IQ values. When you finish, the summation will go to the power of 2. That's the difference between here and here. For b, it will equal the summation of yi minus m. You already found the value of m from here. Multiplied by the summation of xi, all the values of IQs will be having a summation. divide by n, which is the number of samples, which is 20 in our case. This way you found m and b, then y star would be equal whatever value of m multiplied by x minus the value of b, or plus the value of b. Now in this case, our m after doing the calculation would equal 1.0809 for m, and b would be minus 53.67. Now I would say y star, which is the math score, would equal, remember y is the math and x is the IQ. Math score would equal 1.08, which is m multiplied by x, which is IQ, minus 53.67, and that would be the equation for your line or fitting line or linear regression, whatever you call it. Now let's take an example on this point or on this topic. We have a data in this table. They are obtained from measuring the distance dropped by a falling body versus time. Now we expect that the distance should be related to the squared of the time according to the theory. Neglecting the air friction, S would be equal 1 divided by 2 gt squared. Find the equation of the line of best fit. Now we have time, that's t, and we have distance s. Remember, s here is seconds for units, and here m is meters as a unit for distance. When time is 0, distance is 0. And all the way when time is 6 seconds, distance was 176 meters. And you have your equation S equals 1 over 2 gt squared to keep in mind. Now, the expected form of the equation is supposed to be S equals B multiplied by T to the power of M. If you remember, when we did the manual linear regression method, we said there is linear representation and there is exponential representation. Since exponential is not linear anymore, what we do a semi-log drawing or semi-log graph. In this case, we make the exponential to be drawn, instead of being a curve, to be a linear line. So you try to use your mathematical skills to bring it back to be linear. How we do that mathematically? We take the log for this equation, and that means this line would be linear on our semi-log scale. So log of S would equal the M multiplied by log of T plus log of B. Of course, if you're not familiar how that happened, go back and revise the exponential and the log execution on exponent at your convenience. Now, if you use the log of t in place of x and log of s in place of y, you imagine y equals mx plus b in the old format. So we can solve for m and log b. How we do that? So the m based on our equation would be 6 multiplied by the summation of log of t. Remember, how is the main formal equation? So instead of having here xi, it will be log of t. Instead of have yi, it will be log of s, and do the exact same thing as you did here, but instead of x, you have log of t. Instead of y, log of s. You do the calculation needed in this case, then you'll find m to equal 2 eventually. Now, from that, log of b would equal, instead of b, we have log of b. It will equal 9.8558 minus 2 by 2.8 over 6. Log of b would be 0.6. Take e to the power of log of b equals e to the power of 0.69. E to the log of b would be b mathematically. E to the power of 0.69 would give you 4.899. So the equation would be s to equal, we know the b, 4.899 multiplied by t to the power of m. How much m? It's 2. And in this case, you found the linear regression equation that will fit that kind of data for your example. Another example using the method of least squares. Find the equation that best fit the data shown in this table. We have fuel consumption annotated as Q, and we have velocity annotated as V. Millimeter cube per second for fuel consumption, as we're talking about liquid volume, and velocity is meters per second. And you have here when it's 25.2, you get 10 speed. When it's 608, it will be 70. It's more making sense to have velocity first, then fuel consumption, because velocity is the cause and fuel consumption is the reasoning of that cause. Now, what we do as a solution, the data set will produce a straight line if it's plotted on a semi-log graph paper, as we mentioned. Now, the equation will be in the format of Q to equal B multiplied by E to the power of mv. Again, how did we know that this is the format of the equation? If you plot the data on XY Cartesian, you see it's going through a curve. It's not in a, it's almost impossible to do a linear regression for them. Then you know it is an exponent format. You take the len or the log, same thing. Len of Q would be mv, because len of E to the m of V would be mv, plus len of B. Now, examining the equation and the graph paper will lead us to the following. Since the line is straight, the method of least squared can be used. You can't use least square method in a non-linear situation. Or you need to work out your equation to make it linear. Now, we have a uniform scale. The independent variable values velocity in this case may be used without adjustment. Since the ordinate is a log scale, the dependent variable values, which is fuel consumption, must be the logarithms of the data, not the raw data. So you gotta have the lim b or the log b and so on. Now this is the table. Independent variables v, you have v squares, and you have the len of q, you have the multiplication of v and len q. Those formats, you need them to be able to plug in the data in the general format of finding m. Remember, we need to have the summation of v squared, we have the summation of v or x, and you need to have the summation of y, len y in this case, and v multiplied by len q, or x multiplied by y. When you have that, you will easily take those summations and plug them in here. You can see 1494 plugged in here, and you know here you have number of samples is 7, and you continue your calculation, you'll find that m would be 0.05286. Now for the len of b, that would be 33 minus 0.052 by 280 over 7 would give you 2.6. Take e to the power of len b will give you b. E to the power of 2.6 will give you 14.8. The equation will be q to equal 14.8 multiplied by e to the power of 0.053 v. And that's the equation of your line using the least squares method. Now we reach to the golden topic of this chapter, the treasure of statistics chapter, which I call as the coefficient of correlation. Some people call it correlation coefficient. What is it? It is a numerical measure of the statistical relationship between two or more variables. In other form, instead of studying x versus y, in this case, you know how x is differentiating from y. Imagine it as you having two cars connected through a chain. Then if this car is going at a certain speed, that car is going at a different speed. The speed of this car at a certain limit will affect the speed of the other car or the behavior of the other car. So it's important to know how to use the coefficient of correlation. As a real life example, back in time when I was working with Ford on analyzing the data as a data and engineering scientist, we used to jump into the Raptor vehicles and hook up our computers, collect all the data. Sometimes there is a certain behavior that you don't like about the vehicle. It could be engine related, transmission related. Then you have unlimited or huge, you're talking about thousands of variables that play a role in the engine performance and in the transmission performance. Luckily, we have many sensors implemented in the vehicle, which you have access to read those data. So what I would do, I would be collecting data, reading all those variables behavior from those sensors, taking the input as voltage, transferring or translating that into physical values. And you can see how is the crank is doing, how is the power transfer is doing, how is the pressure in the engine is doing, how is the temperature is doing. You have many variables. Now you have a certain phenomena. You don't know who's responsible and which factor is causing that phenomena. You got to limit the points where you want to look at the data to be able to identify and root cause the problem and fix it and move on. Now, the most innovative way, we had a team of 10 engineers, and they all tried to solve it. We had even experts who are like 50 plus years old, and they've been with Ford for 20, 30 years. They were scratching their heads, they didn't know what's going on. I'm not trying to play Superman form here, but what I did, I tried to use what I know most: statistics, mathematics, and physics, and logic behind all of that as an application to engineering. I said, well, I think the best application in this case is to use the coefficient of correlation. So I took that amount, a huge amount of data, maybe it's 10 gigabytes of data, and I analyzed them. I wrote a script for that to be able to analyze the coefficient of correlation between those factors. And based on that, as you will learn about coefficient correlation, you will know how you can easily find the relation between variables. So I was able to squeeze down probably 1,000 variables into 3 only variables, and investigated those in more closely, applied another methodology, and I was able to identify that exact factor is the reason behind this problem, and we solved it, and we moved on, which was amazing. So please pay attention. If you learn only this perfectly from this course, then you are on the right track. Now, of course, correlation will tell you how data are interacting. Correlation coefficient tries to better fit the trend line to the provided data sets. So we said in the least square method, you draw a line. Okay, that's your line. Now, coefficient of correlation can study how those points are related to each other. So it's more realistic. Instead of blindly drawing a line, maybe sometimes you need more precise line. You need to know what's the relation between these 2 points, why they are closer together than these two. So you got to have that in consideration as well. So of course we have, as a general rule, we have positive correlation, we have negative correlation. You can see here increment, decrement, and you can have, if it's a parallel line to the x-axis, then there is no correlation at all. Mathematically, if the difference between the observed y star and the calculated y are small, now the sum of squares, the summation y minus y star to the power of 2 will be small, and vice versa. So when the difference is big, then the correlation, the difference between y and y star, or the sum of squares will be big, then the difference will be big. Now, the equation for the coefficient of correlation, luckily, scientists spend a precious time of their life to come up with an equation that will make you easily implement it and know the correlation between factors. Now, R would equal plus or minus the square root of y minus the summation of yi, remember the observed values, minus y star, which is the calculated values to the power of 2, over the summation of yi minus y bar, which is the mean of the values, to the power of 2. Now, the thing is, whatever value the R will come back with, if R value is close to 0, then in this case, the fit is poor, the correlation is low. While if the R value is close to +1 and -1, then the fit is good. So there's a positive correlation, negative correlation, and there is 0. The closer you are to 0, it's like a horizontal line. There is almost no correlation. Now, this equation used to measure the strength of a linear relationship between any 2 variables or even more variables. If you think about it, you can create more relation between more variables, 10, 20, 100,000 at a time, and look at them. And if you use script and coding, you can even make that more automated and more useful for you. Now, another more widely used form of the equation, the first one was the simplest form. Now, for the coefficient of correlation, can be written as R equals N, number of samples, multiplied by the summation of xi, yi minus summation of xi alone, multiplied by the summation of yi alone over the square root of n, multiplied by summation of xi to the power of 2 minus summation of xi all to the power of 2, multiplied by the square root of n, summation of yi to the power of 2 minus summation of yi to the power of 2 for the summation. Now, general guideline for interpreting the correlation coefficient would be as follows, because when you apply R, you will have always sometimes R as 0.01, sometimes R 0.9, sometimes could be 1, even it's rare, 0.7, 0.5, 0.3, minus 0.3, minus 0.7. So what's the difference between minus 0.7 and 0.7? What's the difference between 0.9 and 0.5? Now, If the correlation coefficient 0.9 to 1, that means it's a very high positive relation between those two variables that you're studying. Now, 0.7 to 0.9, it's a high positive. Like it's a very good relation between these two variables. 0.5 to 0.7, moderate, maybe medium positive relation. 0.3 to 0.5, low relation. Minus 0.3 to 0.3, little if any. So it means most likely this is a gray area that you would ignore. Don't rely on that being a correlation. Minus 5 to minus 0.3, low negative relation. Minus 0.7 to minus 0.5, moderate negative. Minus 0.9 to minus 0.7, high negative. Minus 1 to 0.9, very high negative correlation. Remember why it's minus 0.5 to minus 0.3? Because minus 0.3 in the minus bigger than minus 0.5 and so on. Now, just a side note, R2, so this is the R, coefficient of correlation, R2 called coefficient of determination. Now, you can say 100 multiplied by R to the power of 2% will be used to find Y difference percentage from X. Like how different is value of Y from X? Then use 100 R squared based on the value of R percentage. Then he will tell you, okay, that's 60% different, 20% different, 50% different. In case that's a more representative form for you. But if you are okay, which most people are okay with this format, then you can say, okay, 0.9, that's a very high relation. 0.3, 0.2, that's a low relation between these variables. Please spend some time on this, master it. It's going to be very helpful for you in the industry, and you're going to be the winning card at a situation just by remembering, oh, we can use this kind of correlation. This kind of equation will solve our issue. It can get you out of a lot of research or industry-based problems because only few people know how useful this equation is and how they're going to use it towards the application that they're working on. Example. Now we have water conservation, and they had lack of water for many years. Now, one solution to the problem to construct dams that will allow water storage for large reservoirs. The amount of water flowing into the region is a function of the watershed area, annual rainfall, snow melt, and so on. Assume the dam height, discharge area, and spillways must be designed to accommodate 100 years flood. Now, the data will be shown in the next slide for you. That is the discharge from a river that's under consideration for the construction of a dam as function of recovery time needed to refill the reservoir as given in the next table. These are measurements from the primary watershed of about 5,540 miles squared located southwestern states. Using the least square method, obtain an equation relating the discharge Q and the recovery period. So you got to draw Q versus period, and you find with the least square method the regression line. Compute the correlation coefficient and interpret the results. From the derived equation, compute the projected discharge for 100 years flood. Now that's the table. You have the period in years, and you have the discharge, and you have the period and the discharge again. So the years from 1 all the way to 55.8. Discharge will be 44,800 and so on. Now the solution, spreadsheet is your friend in this case. Of course, you can use spreadsheets to find fitted line using the least square method and be able to find the correlation between data, which is making sense. Of course, you will not do by hand, especially if you have hundreds of thousands of data sets. Now, the data should be entered in columns A and B, as we're going to see next. Test plots were then done to determine visually whether linear semilog or log-log techniques would be the most likely to produce a straight line. So you need to experience with that. You need to do your experiments with that. Now, we can see the log-log plot moving forward, although it would be not straight line. It's near to a linear line, so you can go with that. So we will use the method of least square method to find the equation in the form of Q equals B by P to the power of M, which would be log Q equals M log of P plus log of B. Let's go see that table. So you have a table here. We're going to generate it again together. So column A, B, all the way to H, you have P, Q, log P, log Q, log P, multiplied by log Q, log P squared, log Q squared, and Q star, or Q prime in your textbook, which is the calculated values, which is the Y star that we talked about earlier. Now, of course, you plug in P and Q, then you can easily relate those with equations to find all those values as we're going to do it together. Then you find sum of P, sum of Q, sum of log P, sum of log Q, sum of log P and log Q, sum of log P squared, and sum of log Q squared. I'm going to pull my Excel sheet and start to do that. I'll try to speed it up for you so that you not get bored, but at least you have an idea how did we do that in Excel. And I encourage you to do that on your own as well. Make sure you are comfortable doing that. Afterwards, we'll be able to draw the graphs needed in a semilog or a log-log scale and see how the data is being linear. And based on that, we will be able to define the equation using the least square method. Okay, we get the sheet up and running. So here we have P, then we have Q, then we have log of P, then we have the log of Q, then we have log P multiplied by log Q. Then we have, of course, if you think there's not enough space, you can slide that column to make it aesthetically beautiful. So after we filled all the equations needed, you know, here you put the log of P, log of A2, and you replicate the equation all the way down the table. Log of Q, same thing, log P and Q, so you do multiplication, log P to the power of 2, so you give it to the power of 2, log Q to the power of 2, same concept. Then the Q is equal B multiplied by P to the power of M. You gotta find M and B. So you go down here, you put the equation for M, you go down here, you put the equation for B, and you call them back in here for each value of P. So when P is 1 and the M value and B value are already predetermined, you can find all the values you need, and you will be able to draw the graph and test linearity. If it needs to be log-log scale, you're good. If it needs to be semilog to be able to be linear, then you will be able to add your trend as we learned before, but of course it's not linear now, so you got to create the linear format and put it in the right semilog scale, and you'll be able to draw a straight line and conclude the equation for that line. And that's all about it. And for correlation, of course, in Excel, correlation, C-O-R-R-E-L, then you select the two variables that you want to study the correlation between. You get back a number from 0 to 1. Here it's 0.99, so it's a very positive high correlation. So high relation between the period and the discharge for the dam that we're talking about in our example. And with that being said, you will be able to turn your Excel sheet into a solving tool and correlation studying tool for any two variables or more that you face in your engineering applications.